Hey, good morning, everyone. Hope you all had a good weekend. I tried to get, caught up on my work and my sleep. Could only do one of those. Let's see. Chapter 4 today. So my goal for today is to, we look at chapter 4, the equations that govern the transient period of the voltage in the capacitor energy transfer. And then Friday, I want to cover the examples. Homework will be due Sunday night, and then quiz on Monday. I haven't yet decided whether I'm going to test chapter 3 and 4 together, or just chapter 3 or just chapter 4. I haven't yet decided. I'll decide I'll decide by Friday and let you know. But for now, we are introducing the topic of transient analysis, chapter 4 today. So open up the homework. There are extra credit tutorials. There are also short answer questions and then some problems in there. I won't be able to cover the examples today, but there are certain parts of the homework that you can get done, right? So chapter 4, transients. And I will explain why they are so called transients. All right, first thing is notations. We know inductors and capacitors are noted by L and C. If you have a circuit which has a inductor or a capacitor, we call it, actually, you know what, let me back up. Resistors are part of all circuits. We cannot build a circuit without a resistor. Resistors are what allow us to control the voltage and the current that are present in any part of the circuit. And so if you have a circuit which has a resistor and an inductor, we call it as a RL circuit. A resistor and capacitor would be a RC circuit. And if you have a resistor, inductor, and capacitor all together, is known as a RLC circuit. A RLC. Now, when I use the term one, single, it does not mean that physically it is a single component, right? You could have multiple inductors or multiple capacitors in a circuit, and we could possibly reduce it down to one single inductor or one single capacitor, right? Equivalent. So you could have multiple inductors and multiple capacitors. We would refer to them as one single capacitor or one single inductor, and we just use the subscript EQ, right? Total equivalent capacitor, total equivalent inductor. Similar to how we used REQ, total equivalent resistance, right? So even if a circuit has multiple inductors or multiple capacitors, we would still be able to call it a RC or RL circuit. Okay, RC or RL. So that's the first thing. Second thing, the voltage and current for capacitor and inductor are time dependent, right? L di over dt, C dV over dt. So when we apply KVL or KCL for these circuits, we obtain a first order ordinary differential equation, which I don't know about you, but it's not my idea of a good time. We solve the ordinary differential equation and we obtain expressions for the voltage and current as a function of time. Now we saw in chapter 3 the standard equations for the voltage and current for a capacitor and inductor, right? When a capacitor and inductor receives the energy or sends the energy back into the circuit, it does not happen in an instant, right? We cannot snap our fingers like Thanos and have it just charge or discharge in an instant. So when it receives the energy, we say that a charge is being built up slowly in that inductor or capacitor. And slowly is relative, but it builds it up one charge at a time. And so when it is receiving the energy, we refer to it as charging because the charge is being built up. If the energy is being discharged back into the circuit, we refer to it as the discharge phase or the discharging of that energy. and hence charged and discharged. This is receiving the energy, and this is sending it back into the circuit. Okay, receiving and sending it back into the circuit. So charging and discharging refers to the receiving and sending back of the energy, the receiving or supplying the energy back. Now, as I stated, it's a first order differential equation. So the circuit is referred to as a first order circuit. So RL and RC circuits are referred to as first order circuits. If you have two components that are not reducible, whether they are two capacitors or two inductors, or whether it's one capacitor and one inductor together in a circuit, we refer to it as a second order circuit because it requires a solution for the second order differential equation. And then so on and so forth. Third order circuits, fourth order circuits, all the way up to N. But for the most part, we start with the basics, which is the first order circuit and the second order circuit. For 201, I typically just do the first order circuits. I don't even, we don't even get into the equations for the second order circuits. Okay. And the good news is the solutions were already done. Greater minds than us have come before us, and they have already done the solutions for the basic circuits. And so the equations are all available. I will go through the setup of the problem. I will explain the terms, and then we look at the equations. Okay, we don't have to go through the entire derivation. All right, so that's the good part. Okay, so charging, discharging, first order circuit, and then second order circuits. I'll talk about it a little bit just after we are done with all the examples and everything. But we don't look at the equations. Let's see. When we apply the voltage or a current for the capacitor or the inductor, we know that the response is fleeting. It does not reach steady state. It does not reach the maximum value or the minimum value in an instant, right? So the point in time where it becomes steady with respect to time is known as steady state. But the between phase, meaning upon the application of the input and the steady state, is where the voltage and current has a transient response, meaning the response is fleeting. It is momentary. That momentary time is referred to as transient. Hence the name of the chapter, Transient Analysis. Okay, because we are dealing with transient responses. So transient analysis. And transient analysis is for both DC and AC. But in this chapter, we're going to exclusively look at just DC application of input. Okay, DC input. And for all capacitors and all inductors, it follows a predictable path. All forms of voltage and current have an exponential form. Okay. So this is the voltage and current for a charging capacitor or inductor for that matter. It works for both L and C. It follows a predictable path or a predictable form, which is exponential in nature. So there are three phases in here. There are three phases. Look at the x-axis is time. So this is time t equal to 0. And at time t equal to 0 is the time at which we begin our analysis, right? Again, remember, t equals 0 is always the time or the moment at which we begin our analysis. As we saw in the previous example in chapter 3, t is equal to 0 or t could also be equal to 2. Remember both examples where we broke it up and t equals to 2 milliseconds was the beginning of our analysis. And so that value can change, but here it simply refers to the time that we are beginning our analysis. Okay. Steady state is, of course, the region at which the value is steady with respect to time. And since this is talking about a charging capacitor or a charging inductor, there is a max value that is associated with the voltage and the current. And the max value would typically be the value of the source. So if you apply a 5 volts to a capacitor, the maximum value for that capacitor, the final value would be 5 volts. Make sense? Right? If you apply 1 amp to an inductor, then the final value or the maximum value it can reach would be 1 amp. So after a certain point in time, if we don't interrupt the charging portion, then it will reach 5 volts or it will reach 1 amp. And after that point, it's going to remain steady with respect to time. So steady state. And then, of course, time before the application of the input, the voltage and the current is 0. Now, it may or may not always be 0, and that is what is indicated in this chart, in this illustration. Okay. Typically, for all the examples I use in this class, it's always a completely discharged capacitor or a fully discharged inductor. Okay. So the value of the voltage or the current that is stored in the components is always 0. In real life, that's not necessarily the case. It will always have some stored energy. Anyway, so the point at which we begin our analysis is referred to as t equals 0. So prior to the value of time equals 0 are known as the initial conditions. And they are referred to by the subscript I. This is not I for current. This simply stands for initial. And so initial conditions could be VI or II. It is also referred by the subscript of 0. And 0 here refers to the time t equals 0, meaning the point in time at which we begin our analysis. And so it is also referred to as V0 or I0. And I will have both in the equations in my slides. Okay, so if you see 0 or I, it is referring to the initial conditions right before we begin our analysis. All right, makes sense? And then we have the initial conditions, we have the steady state conditions, and the time in between is what we're interested in. And this is what we are studying in this chapter, the transient response, where the voltage and current is changing with respect to time. And so all our equations will be a function of time. V of t, I of t, P of t, instantaneous power at any given point in time. All three quantities, voltage, current, and power, as functions of time. All right, questions? So far, so good? One more point before we move on. So both these charts illustrate a charging portion. Discharging is also exactly the same. If charging goes like this, discharging simply goes like this. Charging, discharging. And the beauty of this is that it's all exponential in nature. Whether it's charging or discharging, they're all exponential. Okay. All right. So transient response are of two kinds, natural and forced. And it's not as sinister as the word sounds. Okay. Forced, let me address forced first. Forced or step response is basically in the application of an external input, which is all we have seen so far. When you apply a source to a circuit, you're forcing a response from that circuit because that source is external to the circuit, right? So again, as I said, it's not as sinister as the word is. Forced is basically the application of an external input, meaning it's not part of the capacitor or part of the inductor. And essentially, that's what you have done. Chapters 1, 2, and 3, we have a source, we connect it to a resistor, and the resistor voltage or resistor current is due to the application of the external voltage or current. And so a forced or a step response is basically you're applying an external input. The external source or external input causes the current or the voltage in that capacitor or inductor. So basically, it is sending the energy into the inductor and the capacitor, right? Capacitor and inductor are receiving the energy. And the natural response is the exact opposite. There is no external input or no source connected. Okay. No external input and an external input. So natural versus forced is simply referring to the charging and the discharging phases. That's all. So there are 4 circuits we look at. We have natural and forced response for both RL and RC. Okay, so we have natural response for RL, natural response for RC, natural response for forced response for RL, and forced response for RC. So 4 different circuits, but they all have exactly the same form. Okay, and we won't, we are not going to go in depth. We're not going to look at how it's derived because it's more important for you to understand what to do with the equation once you have it. Okay, and we'll start with natural response first. So natural response circuits, simply RL or RC. You take all of the resistors in the circuit, you take all of the inductors in the circuit, you take all of the capacitors in the circuit. If we can reduce it down to one single R, one single L, or one single C, it is still a first order circuit. We have a RL circuit or we have a RC circuit. The EQ simply notes that if there were multiple components, then we have reduced those multiple components down to one single component. Simply find EQ. Subscript EQ, the total equivalent value. Okay. So again, RL is simply LEQ and REQ, and capacitor CEQ and REQ. In this case, for a natural response, all we are doing is we have a charged inductor or a charged capacitor, and it is simply releasing all of its energy through that resistor. It's just discharging, and that's it. Okay, a charged or basically a fully charged inductor or capacitor has stored energy, and that stored energy is slowly released through that resistor. The resistor dissipates their energy as heat. A real life application would be like a camera flash, especially the professional ones that are stuck on top of the off top of the camera unit. You have sometimes you have 3 or 4 AA batteries. Once you use it, you might have heard like a tiny whining noise. That is basically the capacitor inside it being charged. Okay. So again, from a battery supplies constant voltage or constant current. But for a light flash, we want all of that energy released all at once, hence flash. And so the capacitor charges stores all that energy. When you press the camera picture button, all of that energy is released all at once. And so the light bulb in this case is the load and not the resistor. All of that energy is sent to that light bulb all at once, flashes once, and all of that energy is gone. And then it begins charging again. A lot more complicated than that, of course, but that's the basic operation. Okay. So that's the natural response circuits. If you add a source to it, we get the forced or the step response. Okay, forced response. So source, source, and source. This is simply the Norton current IN. How many of you are taking the lab? Almost all of you, right? You're done lab 5. Pretty much everybody should be done with lab 5 now. So you had a circuit at the end in procedure 2 where you did, where you had an inductor and a capacitor in there. The first one was rather simple, one resistor and one capacitor. The second one, and there's a point to this, the second one, there was one source. You had an inductor and a resistor. I'm not drawing the inductor for now. Then you had a capacitor here, and you had a resistor there. And let's say this was 10 volts being applied. Okay, so if you had a circuit like this, 10 volts being applied to that capacitor. Or is it? Are we applying 10 volts to the capacitor? No, because the 10 volts is being applied to the capacitor through these resistors and through this one also, right? Current will flow through this resistor to all 3 resistors, and the voltage, some of the voltage of 10 volts will be dropped across these 2 before it goes to the capacitor. If you remember the values, the capacitor was like 0.74, less than 1 volt. Okay, less than 1 volt, because a lot of the voltage was being dropped across the inductor. The point is, if you have a source, simple circuit, you just have a source, you have multiple resistors, and you have one single capacitor, that 10 volts is not directly applied to that component. So you have to find the Thevenin equivalent circuit as seen from the perspective of that capacitor. So you'd have to reduce the circuit down to its Thevenin equivalent. And that is another application of the Thevenin or Norton equivalent circuit. I believe I had mentioned it at the time that we would see this in chapter 4. Okay, just an application. I won't make you do like a complicated Thevenin derivation there. Okay. But the point is an important point that you have to keep in mind. When you have a large circuit like this, and you might have more than 1 or 2 sources in there. So the actual voltage or the current that is being applied to the inductor or the capacitor can be determined only from the Thevenin or Norton equivalent circuits. So you'd have to find the Thevenin equivalent circuit as seen by the capacitor. Okay, that's just a point to keep in mind. All right, so that's the step response circuits. Let's actually look at the equations. Okay, we'll start with RL, then we'll look at RC. Now, the concepts here that you need to be aware of, basically, the first thing we look at is the switch. The concept of switch is used to indicate the point in time at which we begin our analysis. Okay, it may or may not be a real life physical switch, but for the purposes of analysis and explanation, we represent certain events as the flipping of a switch. Sometimes there's a transistor in the circuit that turns on and off. Again, it's digital. And so we represent that as the flipping of a switch. In this case, there is a time that is associated with that switch. And it means that at that particular value or that particular moment in time, the switch is changing functions. The switch is changing states. And in this case, the state is noted by the arrow. So taken together, that simple symbol along with that simple arrow symbol, along with the time listed on there, means that at time t equals 0, the switch is being flipped open. Okay. At time t equals 0, the switch is being flipped open, which also leads us to conclude that prior to time t equal to 0, the switch was closed. Okay, two important points. At t equal to 0, the switch is being flipped open, meaning prior to t or t less than 0, the switch was closed. So I can draw it out this way. And this is very important because when the switches are flipped open or closed, the circuit changes. And the first step in any problem that you solve will be redrawing the circuit. You have to redraw the circuit based on how the switch is flipped. Now for E major class, we devote like 2 whole chapters to these transient analysis, and where there are like multiple switches in a circuit, and the switches flip at like 1 second, and then 5 seconds, and 7 seconds later again another switch flips. So a lot more complicated. But again, that's for E. So if you have an E buddy, you can definitely ask them. We won't do anything of that sort in this class. Okay. Again, we are simply snorkeling the surface. We're not going inside. Anyway, time t equal to 0 again is simply the time at which we begin our analysis. When the circuit flips either open or closed, circuit changes, we need the value of the voltage or current right after the switch is flipped. Okay, right after. So the second point or the second concept here is of t plus and t minus. Right, t plus and t minus. And it simply indicates, plus simply indicates the time right after. Right after or immediately after. Immediately succeeding. And then minus simply indicates the time right before. Or immediately before or immediately preceding the flipping of the switch. Okay, so 0 plus and 0 minus simply indicate the moments in time that are right after or right before t equal to 0. Yes. Not always. The switch could be closed before, or could be open before. T equals 0 is simply the point in time at which we begin our analysis. In this example, the switch is being flipped open at 0, but it could also be that the switch is always open before 0, and at 0 the switch is being closed. It's yeah, it could be open, it could be closed. There's also multi-pole switches. As I was referring, EE classes, we have examples which have like, you have t equal to 0, it's connected here, and t after 0, it's connected there. Or you could have multiple positions. So at 1 second, it's at position 1, then it moves on to position 2, 3, 4, 5, 6, 7. So it could be anything. But it's a good question. So it's not always closed, it's not always open. It just depends on what the circuit gives you. In this particular example, it is shown that t equals 0, the switch is being flipped open. But it could also be being closed. Yes, there was some, yes. I will explain. But is everybody clear with the concept of 0 plus and 0 minus? Okay. And it's important because we need to establish what the maximum value of that stored energy is, either in that inductor or capacitor. And that's why. Okay. All right. So the next question being asked was actually going to be my next point. Why there is no current through the resistors? Where this example assumes that the switch has been closed for a very long time. So if you read the words a very long time, it indicates that the system was already at steady state. Okay. So a very long time or very long time indicates the system is at steady state. And so most of the problem statements will always have, oh, the switch has been closed for a very long time, or the switch has been opened for a very long time. It simply means that the system is at steady state. Whether it's fully charged or fully discharged does not matter. The system is at steady state. So in this case, for t less than 0, it has been closed for a very long time. If the switch was closed for a very long time, it was a short. After the initial period transient portion, the inductor starts to receive the charge, right? After a certain point in time, sufficient time has elapsed and the inductor has reached full charge. When the inductor reaches full charge, it behaves like a short circuit. And so if it behaves like a short circuit, all of the current is only going to flow through that inductor. And if all of the current is flowing through the inductor, nothing is flowing through the resistors. And that's why. So the key word here would be a very long time. Okay. So these are the initial conditions. These are the initial conditions in the circuit. And you have to understand or extract all of that information by looking at the circuit itself and reading all of the information that is given to you. So the information would be in the circuit diagram as well as in the problem statement, right? A very long time indicates the system is at steady state. If the switch notes a time, t equals to 0 or t equals to 5 seconds or 5 milliseconds for that matter, then your initial portion of analysis begins at t equals 5. For this class, it's always going to be t equals 0. And then you establish the initial conditions. You find the values of the voltage and current at 0 or right before 0, because that is going to be the same as right after 0. Yes. After we open the switch? No, that's what we're going to look in the next slide. So the circuit changes. Well, once it reaches steady state, all the current is still simply flowing through that inductor. Now, this is a very, very simple representation. In real life, if you have a short across a source, what will happen? Sparks. I mean, you just blow out your fuse. I mean, light would go out, right? Because there's a short across the source. So we always have a resistor in series somewhere. But this is just we simplify the circuit just so that we can explain the derivation of the natural response. Okay. All right. So t less than 0, the inductor is fully charged. Because it's fully charged, no current flows to the other two resistors. And then the switch is flipped open. When the switch is flipped open, the source and R0 are disconnected from the rest of the circuit. Okay, switch is open, the source and the resistor are disconnected, and the circuit, after I redraw it, looks like this. Simply the inductor, the fully charged inductor, and the resistor on the right. Actually, right or left does not matter, but for the illustration purposes, I do it on the right side. So you have a fully charged inductor, and here's why the 0 plus and 0 minus are important. We know the current through an inductor or the voltage across a capacitor cannot change instantaneously, right? So if we look at this circuit, we don't know what the current value is. We don't know what the current value is. We will have to determine that value from the time t less than 0. Time t less than 0, which is the value of Is. That's the source that is flowing in there. The full charge that is stored in the inductor has a value of I0 because the current to an inductor cannot change in an instant. So the current at 0 plus, which is right after the switch is flipped, is exactly the same as the current at 0, which is also exactly the same at 0 minus. Meaning the current right after the switch is flipped is equal to the current that was right before the switch is flipped. So I0 plus is equal to I0 minus, which we refer to as II or I0. II or I0. The initial current or the current at time t equals 0. Either notations are fine. And that initial current had a value that is equal to the source current Is. Yes. Sorry, what? Yes. So the inductor starts discharging through that resistor. And that's how we will do the derivation. So there is no source in the circuit anymore. It's a fully charged inductor that is now releasing all of its energy through that resistor. So it's a discharging phase, and we will write equations by applying KVL at the top. It's two components. There's simply VL plus VR equals to 0. VL is L di over dt. And we have a first order ordinary differential equation. Now, different circuits will have different differential equations. And so the job of an engineer would be to actually look at the circuit, determine the initial conditions, and then write a solution to that differential equation. So there is a derivation in the book if you're interested. There are many books, there are online resources. I can point you in the right direction if you wish to look at the derivation. If you can't sleep at night, it's a good way of, getting some Z's. But as I mentioned earlier, greater minds have come before us. They did they solved this differential equation and they provided a solution to us. The important quantities in these solutions are noted right here. We get the value of the current, not value, sorry, we get an equation for the value of the current as a function of time. So I of t is given by I0 into e raised to minus t over tau. It is simply I0 and e raised to minus t over tau, where tau is the Greek letter tau, is the time constant of the circuit, describes the rate of energy transfer. In this case, it is discharging, but tau is also the same for a charging circuit, meaning when it receives the energy and when it discharges the energy, the time constant is exactly the same. It is known as a constant because it depends on the physical values of the inductor or the resistor and the resistor. Size of the bucket and the flow of water. Right? Size of the inductor and the resistor. So the rate at which it fills up or the time it takes to fill up depends on the size of the bucket and the flow of water, which is the resistor and the inductor. So it's always a constant for that particular circuit. Okay, it's given by L or R. And you can have all of these equations in your equation sheet. You don't need to memorize them, but once you solve quite a few examples, it becomes ingrained. You'd be able to recognize it quite easily. So let's take a look at the equation. What do we have? We have I0, right? I0 is the max value. I0 is the max value. So if you plot this at time t equal to 0, meaning when we began our analysis, the value of the inductor current I of t would be right here. I0, right? The max value. And from that point, it's all downhill, right? It's discharging. So it's losing all of its energy, except it's not linear. It always follows an exponential form. So e raised to minus t over tau, t is the variable. If you plug in t, t could take any value, right? Because this equation describes all values of t. But if you plug in t as one-time constant, tau, if t equals 1 tau, you get e raised to minus 1, which comes out to be 0.6321. No, actually it comes, wait, e raised to minus 1 is, I'm saying the other way around. Am I saying it the other way around? E raised to minus 1 is 0.63 or 0.37? 0.63. After one-time constant, the capacitor loses 63% of its value. So it is the other way around. It should be 0.37. Let's see, calculator. Anyone have a calculator handy? What is e raised to minus 1? Right? 0.37. Because it's multiplied with I0. So 0.37 times I0 after 1 tau would be somewhere here. Let's say this is about 50. Let's call this about 60% approximately. So 0.37, 1/3 and just above 1/3, maybe about here. So this would be 0.37 times IO or I0. So after one-time constant, the capacitor loses 63.21% of its charge. More than half of its charge, it's gone after just one-time constant. And so the value would be somewhere here. Let's say this is 1, 2, 3, 4, 5, and so on and so forth. So the value would be somewhere here, and then here, and here, here, and here. And so when you join this, you get something like this. You don't have to draw this out. There's a nice chart at the end of this presentation, at the end of this chapter. It shows both charging and discharging on the same graph. But I just wanted to point out that no matter what the value of I0 is, it could be 1 amp, it could be 5.5 amps, it could be milliamps, microamps, it doesn't really matter. If you have a RL or RC circuit, it always follows an exponential form. Okay, always has the exact same form, whether charging or discharging. Now, this equation, as I said, describes the transient portion, right? What happens after a certain period of time has elapsed? What happens to all of that energy? It's all gone, right? It will all be gone. But mathematically speaking, if you plug in any value of t, you would still obtain a value for the current. You could plug in t as 1 million seconds or 1 million hours or whatever. You would still obtain a value for I of t. 0.000000000, so on and so forth. And at the end, you might have some digits. But for all intents and purposes, it's fully discharged. Mathematically, this does not describe everything because it can never go to 0. Does that make sense? So when do we put a stop to it? 5 times tau. I thought you all took the lab. 5 times tau is generally accepted convention. 3 times tau, 4 times tau, and 5 times tau. When you plug in e raised to minus 5, it goes less than 1% of energy remaining. Okay. So more than 99.3 or 99.5% of the energy is already discharged. And so after 5 times tau, we say it is fully discharged. As well as if you're talking about charging, we would say it's fully charged. Okay. We good on the equation? Right? And again, if you took the lab, this equation was there in the lab write-up. Solutions for voltage, power, and energy are the same form. Voltage given by Ohm's law is V equals IR. And so V of T would simply be I of T times R. You simply plug in the value for I of T. Instantaneous power, P equals VI, or in terms of the resistor, it would be I squared times R. And so P of T is I of T times R. And then total energy dissipated in the resistor, again, there's a derivation for this, but it comes out to be exact same equation, half Li square, which is what we saw in chapter 3. All of that stored energy in the inductor has nowhere else to go. It is going to get dissipated in the resistor. And so the total energy dissipated in the resistor is basically half Li square. I is basically the initial stored current in that inductor. So you get Li0 square over 2, or half Li square. All right, makes sense? Okay. I have about 3 minutes remaining. And so let's quickly look at the capacitor equations, which again are exactly the same. The model, the circuit model is also the same. The switch is flipped from the left to the right. From the left, this is just a different way of showing that when the capacitor was connected to the source, it charged up fully, right? That full charge would be equal to the value of the source. In this case, it is noted as VG. G just stands for generator. It could be any subscript. Does not really matter. And then at time t equal to 0, the switch is flipped to the right. When you flip the switch to the right to position B, the source and this resistor R1 are disconnected. The only things left in the circuit are the capacitor and the resistor. It's a fully charged capacitor, has a value of VG. Capacitor voltage cannot change instantaneously, meaning the voltage right before and right after the switch is flipped is exactly the same. So the initial conditions for this charged capacitor indicate that V at 0 plus is the same at 0 minus. We refer to that as the initial voltage V0 or VI if you want, which is equal to the source voltage VG. The source voltage could be anything, 1 amp, 1 volt, 5 volts, 10 volts, could be anything. To solve for this first order circuit, we apply KCL at the top and we obtain IC plus IR equal to 0. IC is of course C dV over dt. IR is V over R. Again, we have a first order ordinary differential equation. We solve that and we obtain the exact same equation. V of t is V0 into e raised to minus t over tau. No difference. Okay, no difference. When you plot this, you again obtain the exact same form. You start at V0 and then you slowly but surely reach steady state of 0 volts. Tau in this case is very easy to remember. It's a product of the resistor and the current. So for RC circuit, time constant tau is RC. That's it. For RL, it's L over R. Yeah, it might take you a few seconds to remember that, but for RC, it's rather straightforward. And time constant remains the same for charging as well as discharging. That does not change. Okay. Oh, wow. I'm out of town. Out of time. Equations are also exactly the same. If you have to leave, you can leave. I'll just record the last bit and put it online. And so I is V over R. And so I of t is also V of t over R. Instantaneous power P. P is VI or V squared over R. And so P of t is also V squared t over R. And then energy discharge in that resistor is the total stored energy in the capacitor. So half CV square. And the voltage in this case is the total initial stored voltage in that capacitor. And then one final thing is a summary slide for natural response. The first thing you would do is to look at the circuit and the problem statement, establish the initial conditions. You would reduce the circuit and redraw it. So redraw after the switch is flipped, and the reduce refers to the total equivalent component, total equivalent values of those components, okay? REQ, LEQ, or CEQ, or the Thevenin voltage and Norton current. Establish and find the initial current and voltage, find the tau, and then directly plug in the values in these equations. And then that's it. That's the solution for a first order circuit. All right. Okay, so we'll end class here today. Yes. Yes. Yeah. And in this case, it's a discharging circuit, so the steady state is 0. Yeah. All right, so we'll end class here today. We'll pick up here on Friday. Again, I will urge everyone to open up the homework and take a look at it and start solving, well, not answering some of the short answer questions.